So welcome everybody. It is my great pleasure to have this opportunity to introduce today's speaker, Professor Sabino Matarrese from the University of Padua. Professor Matarrese got his PhD in 1982 from the International School for Advanced Studies, CISA, in Trieste. Soon after his PhD, he became a professor at the University of Padua. And Professor Matarrese's research spans a wide range of fields in cosmology. In particular, he has made pioneering work in inflation, relativistic perturbation theory, primordial non-Gaussianity, CMB anisotropies, dark energy models, and galaxy bias. Basically all areas in theoretical and observational cosmology. So I'm sure that all of you working in cosmology must have come across Sabino's papers in the past. So as such, without further ado, I'm very happy to have him here online today. And he will tell us about what he has been up to recently. So please, Sabino.
Thank you very much, Ayun, for your very nice presentation. And I'm going to give a talk, which is basically sort of a view of various aspects of my recent research, finding out a sort of connection between various fields, which at the end of the day, I've been thinking about that for a long time. I said, well, at the end of the day, what is connecting various parts of my research? And for maybe 90% of what I did, I mean, nonlinearity in cosmology is the common denominator of what I did. I'm trying to show you in which way these things are connected, which especially I'm going to pay attention to possible future research topics in this connection. Okay, so first of all, okay, so let me tell you that of course the simplest approach to cosmological observables makes use of a background solution, which we like. The idea of being made of a three-dimensional work standard cosmological model plus small linear perturbations superposed on that. Okay. Since I don't think I will have more time on this, let me just mention something in that respect. Okay. Of course, we all love the idea that the universe, on very large cases, is isotropic and homogeneous, but I still believe it's important to open our mind to possible alternatives. Sometimes these alternatives look so different from the work that we don't like them, okay? But I think it's very important for all practical purposes, even data analysis and in the interpretation of data analysis, to assume that in principle you may have other opportunities, other backgrounds, and if you allow your data set to include these extra backgrounds, then even though the best fit model is always okay, that would have a change in the error bars or parameters, etc., etc. So please keep your eyes open on alternatives. If you, at the end, if you like, you can say something more in that respect, which kind of ideas I have in that respect. Now, one the need to go beyond linear theory is universally recognized when dealing with cosmic transformation, because of the well-known James instability. There are several other consequences of going beyond the linear level, which have become a standard law in cosmological analysis only during the last 20 or 30 years, and others which are still very poorly understood and explored, which I'd like to emphasize today. So I plan to review several examples of deviation from linearity. First of all, non-Gaussianity, of course. Then, second of all, not necessarily in the right order, the production of gravitational waves from density fluctuations, that is from scalar fluctuations, the production of magnetic fields from density fluctuation, which appears less obvious, the production of density perturbations out of gravitational waves, which is our latest directional research, and quite interesting, unexpected non-vanishing cross correlations among seemingly independent observables because of linear effects. Then, as I mentioned, we all accept the idea that nonlinearity plays a role in the elastic structure formation. When you see a map like this, and you see very huge structures in that, you say, well, that's not a surprise. I mean, we do see by eye phase coherence, and we do assess this phase coherence to, ascribe this phase coherence to non-linearity, which is intrinsic in the gravitational interaction. Okay, but on the other hand, when you look at the CMB sky, to a very good approximation up to reasonably large values of the L or the harmonic index, we know that a linear analysis accounts for large fraction of what we observe in the sky. So we have this twofold situation. For elastic structure, we like the idea of non-linearity. For CMB, we can relax and say, well, at the end of the day, most of the results can be obtained by linearity, which is, of course, simpler. And in a sense, we have a better control of the parameters or the difficulties which give rise to the final result. Okay. So the need for linearity it can be understood like that. The very existence of cosmic structures, the elastic structure of the universe, and even the visual impression of the cosmic wave, as I mentioned, is evidence for underlying linearity. Indeed, in those cases, we advocate the well-known James instability. By looking instead at CMB sky, we may easily guess that such tiny temperature anisotropies may be explained by purely linear perturbations. Nonetheless, there are many effects which need going nonlinear, small-scale effects like Sunayat-Zadovich, Vizhniak, Rishama, and others, and non-Gaussianity even on large angular scales. The common understanding of that, if you want to speak to a non-cosmologist, you want to focus on the connection between linear and non-linear level, the jargon, as we all know, is the following. Gaussian is equivalent to a free non-interacting field. Non-Gaussian, which in Fourier space is equivalent to, say, phase coherence, is equivalent to non-linear, in this case, driven by gravity, non-linear dynamics, and or non-linear initial states, initial conditions in the cosmological case. Okay. Okay, let me just make a historical remark about the James instability phenomenon, which is quite obvious to all of you, but I want to do it because I want to insist on some important points. Okay. In an important article in 1902, Sir James Jeans analyzed the evolution of perturbation is a self-gravitative medium. He assumed a static background solution with constant uniform density, pressure, and gravitational potential, as well as with vanishing velocity in the background. The treatment adopted by James is internally inconsistent. As we all know, the dynamical equations do not admit static solutions and call for a time-evolving background. In spite of this inconsistency, he found that perturbations above a certain scale, that's called Jeans length, exhibit an instability, which has been later dubbed James instability, which leads to an exponential growth of perturbations with a time scale inversely proportional to the square root of the fluid mass density and comparable to what we know now is the Hubble time scale. Once this is consistently solved, the instability remains, but now it is found to evolve in a weaker power law form because of the expansion universe. Hence, the qualitative conclusion by this was correct. Only the quantitative one had to be corrected. The Jeans gravitational stability is known to be the cause of structure formation in the universe at any scale. A homogeneous and isotropic universe, and though the tiny initial perturbation is unstable, that is the point which I really want to mention. I don't remember where exactly, but I know that Jim Peebles stressed many times this aspect. I mean, Robertson's work is unstable. If you just perturb it, you go towards something much more complex, such as the universe that we are familiar with, which is endowed with structures and basically all possible scales. I want to mention something in that respect. I wrote a paper 3 years ago with a former student of mine, Alexander Gans, who is now in Krakow, Purnendra Karmakar, also from a student who is now in Japan, and Dima Sorokin, who is in my department, and by studying mimetic gravity. In the mimetic gravity scenario, sometimes people say, "Oh, it doesn't work." It doesn't work because in many cases you find instabilities, okay, which is absolutely correct. But there is no instability which is unavoidable, and which has to be there. in the case if you to add matter, which is the instability, which in that case appears in a sort of tricky way, so you don't recognize it that immediately. And then that was one of the points that we made. I mean, be aware that you shouldn't give up to this instability. It's not a problem of the model. It's something that should be there. We did find it. Okay. As we all know, lambda CDM model works very well. That was the motivation for Nobel Prize given to Jim Peebles a few years ago on all possible scales. Okay, and the lambda CDM model contains a number of ingredients. Number one, the background model, which, as I said, works perfectly well, which is not a good reason to not to think about alternatives. GR plus quantum matter, plus a cosmic constant, plus baryons, radiation, 3 large mass neutrinos, etc., etc. Okay, and it takes care of most of the observations that we are aware of today. And then there is another ingredient, which is the initial conditions, inflation, which gives rise to the density perturbations in gravitational waves. Okay, so let me spend some time on inflation because I want to emphasize where nonlinearity ends in the game in this case. Inflation is a self-consistent model of the very early universe. It is the generator of cosmological perturbations that give rise to CMB and isotropies and last structures. And most importantly, the inflation model predictions have been already confirmed by several observations, even though we are still trying to get the so-called smoking gun proof of inflation in terms of gravitational waves. You should always remember that inflation works very well and makes predictions which have been confirmed, which at this moment is very difficult to get by any other model of the early universe. That is a very standard plot in which you see how inflationary models compare with observation data that is from the Planck correlation to which I belong for 20 years. And you see that the best fit model is basically a Starobinsky model, which is can be understood as a sort of modified gravity model in the early universe. I show this plot also because this dashed line here is my model of power law inflation with an exponential potential, which is still shown in plots. Unfortunately, it doesn't work. It doesn't work. It doesn't fit the data because it is so predictive that there is a one-to-one connection between the scalar spectral index and the tensor to scalar ratio, which is unfortunately at odds with observation, even though there are variants of the model which relax this constraint and allow you have a better fit with the data. Okay. As far as inflation is concerned, at some point, I would say in the mid-90s, more or less, we understood that we had to go beyond linear theory. And there was this important statement that I always used to make in my seminars, which is the leading contribution to higher order statistics, such as by spectrum, which is the Fourier transform and three-point function, comes from second order metric perturbations around the working background, unless the primordial Gaussianity is very strong on its own, as it happens in some multi-field models of inflation or models with non-canonical kinetic term, even in the single field case. In all cases, we have to accept the idea of going beyond linear theory. There was this very nice sentence made in a paper by Sachs and Wolf in 1967, very important paper that they wrote, and in which they say the linear perturbations are so surprisingly simple that a perturbation analysis accurate to second order may be feasible. That was their prediction in 1967, then became an industry towards the end of the 90s. Let me say something about the level of Gaussianity in the simplest possible way, okay? We at some point, let me tell you that since I started working on these sort of things very early, basically in the mid-80s, okay, I wrote some papers on Gaussianity in X structure. At the time at which there were very, very few papers in this direction. I had many discussions with people, especially like Sergei Shandarin or Lev Kaufman, And they gave me a very nice sentence, which is due apparently to the Dovich, who says, okay, we know perfectly well what the Gaussian is, but we don't know what the non-Gaussian is. Okay, so non-Gaussian is like non-dog, because it opens up a Pandora box of many possible possibilities. And indeed, at the very beginning, we didn't know what to do. So we started to look at, chi-squared models, so things very log normal models. In the end of the 80s, I wrote some papers, my colleagues in Padua and Bologna, in which we made some n-body simulations with non-Gaussian initial conditions, but we didn't have any preferred models, so we just explored very non-Gaussian models, okay? We did have that possibility to explore a very Gaussian model because the quality of the data at the time wasn't comparable to what we have today. So there was much more freedom into the initial condition that we have today. Then at some point, that happened more or less at the end of the 90s in a series of papers, which I quote here. Okay, people said, wait, why don't we just make a sort of Taylor expansion around the Gaussian case? And that was the time which people introduced the parameter FNL with some different names at the very beginning, and GNL. So FNL multiplying quadratic non-Gaussianity, and GNL multiplying cubic non-Gaussianity. So we say I have a Gaussian field, phi L, and then I may go to phi L squared, phi L cubed, etc., etc. Then you can rearrange these parameters in a better way, frankly. And what happens is that if you try to constrain these parameters from the data, you unavoidably arrive to numbers like that. Remember that the percent of non-Gaussianity should account for the fact that even though FNL is dimensionless, okay, there is a sort of intrinsic phi L root mean square value to be taken into account. So if you account for that, you see that the non-Gaussianity percent is phi L root mean square, which is 10 minus 5, roughly, times the absolute value of FNL, and we get something like 10 to minus 5, because we know that nowadays the constraints are around unity, and that you have a very similar situation for GNL, which both boil down into say that the amount of excitement which is admitted in this kind of models, okay, in this kind of models is very poor. Remember that in principle, you may invent completely different ways of looking for Gaussianity, in which you may have more freedom. Of course, it's not easy. It's not an easy task, but it's not impossible. Let me spend some time about this, let me say, simplest idea of nonlinearity, of non-Gaussianity, and to tell you what the situation is in that respect, to summarize the situation in that respect. Parametric non-Gaussianity probed fundamental physics during inflation, being sensitive to self-interactions, interaction of fields present during inflation, because different models predict different amplitudes and shapes of the pi spectrum, okay? And the standard models of zero inflation predict only a tiny deviation from Gaussianity that was repeated in many papers. I like to remember this paper that we wrote in 1995 with Alejandro Ganghi, Francesco Lucchini, and Sia Moirac, which used stochastic inflation techniques to arrive to the final result. And the final result is of the same order of magnitude of all the following papers, only some coefficients were different. And we had this paper in 2003, and then for a couple of months, Madassina had this result. The Acquaviva et al. Paper, Madassina paper, reached very similar results. The coefficients are different because in our paper we made some excessively strong approximation, let me say, okay? By removing this approximation, even though techniques are completely different, we should have got exactly the same results. It was shown later by other people. Okay, it's important to say that even in case we decide, okay, we do like the standard models, okay, and we do accept only this source of Gaussianity, that is in perfect agreement with Planck data, Planck constraints on Gaussianity, okay? Then, of course, primordial Gaussianity also pros much more extreme modes of Gaussianity, but we should remember that the constraints are so strong that we don't really have so much freedom as we expect, okay? The model which I showed at the beginning was assumed FNL to be a number, a constant. Then later on people said, well, in principle, it can be a function value of space or with number, depending on whether you are in configuration space or in Fourier space. And that showed in a number of papers. I remember the one by Babish et al. In the beginning of the 2000, that gave rise to the definition of various shapes. The one in which you have a constant FNL is called local non-Gaussianity, which is maximized by squeeze configuration. The bispectral is the bispectral, which is the Fourier transform of the different function, is maximized for one of the wing numbers, which is much smaller than the other two. Then you have equilateral non-Gaussianity, which is typical of single field models with, let me say, for instance, non-canonical kinetic terms, and orthogonal non-Gaussianity is also there in those models, and many, many others. In principle, you may have an infinite number of non-Gaussianity shapes. Let me show you the results. That was obtained in the Planck collaboration, making use of what's called modal decomposition, which is basically an expansion of the bispectrum in the space of possible shapes. Okay, and what you see is that these are the various possibilities. Sorry, temperature, E mode, TPE, and EET, and this is what you find. Then, of course, you have to interpret these results, and that gave rise to the following constraints. Let me look directly at the final result, the most important result, which tells you that local is consistent with 0, with an error bar of 5.1, 1 sigma. Okay, equilateral is also consistent with 0. If we go to the center of -26, plus or minus 47, and orthogonal is -38, plus or minus 24. That's 1 sigma. So all of them are really consistent with 0 to sigmas, as we do expect. Okay, this is one of the techniques that we use to probe non-Gaussianity. It's called Komatsu, Spergel, and Vandert representation. And we found very, very consistent results with all possible techniques. At the end of the day, what we can say is that standard deviation is still a good model. And when I say standard deviation, it just means single scalar field, single clock if you prefer, canonical kinetic term, Zorro dynamics, Bash-Davis initial vacuum state, and Einstein gravity, which do predict that tiny amount, 10 to minus 2, even less according to some other people, but I disagree on this statement. So 10 to minus 2 primordial signal, which of course we are not yet at the level of being able to constrain. Okay, so no presently the type of primordial anxiety according to these models. I should really mention that I spent a huge amount of time in this project together with Ben Bunt, being the leader of the non-Gaussianity project in the Planck collaboration, and very proud of the results that we obtained. That's pretty well now. It's 4 years ago, the last result, but 3 years ago actually. It's very important that they are still the best constraints that there are on the market. If you go to Lasser structure, the situation is of course complicated by the fact that there is intrinsic non-Gaussianity owing to the G stability. Of course, it's the most modern way. You can do something very similar. Remember that phi is related to delta this way. There is a tricky issue which I prefer not to enter in the discussion, which is there are different conventions. In a sense, it would be better to use the comoving curvature perturbation zeta rather than phi, but historically phi was the variable chosen, so I prefer to remain to this historical statement in such a way that I have FNL and not FNL multiplied by extra parameters, but of course, you know how to go from one quantity to the other, so there's no reason to complicate our life, okay? Searching for non-Gaussianity in the Gaussian clustering situation, okay? Now, an important point, which nowadays is obvious to everybody, but frankly wasn't obvious at all when people started to look at non-Gaussianity in structured data, is that besides using statistical estimators like the mass by spectrum, trispectrum, 3 and 4 point function, because at the end of the day, there are techniques which allow you to to see directly the matter distribution, okay, one can look at the tensor distribution that is relevance or peaks. Remember that when you have something non-Gaussian, where something non-linear, the nonlinearity is going to be emphasized if you go towards the tails, much more than trying to constrain the bulk of distribution, okay? But we are fortunate because if you rely, for instance, on pressure theory, the linearity of this type, we know that galaxies correspond to rare events of the entire distribution. So the whole set of the observables that you have to deal with in the case of galaxy clustering has to do with rare events. That is very important. Okay, so rare events have the disadvantage of being rare, but in this case, that is all what you have. Okay, but they have the advantage of emphasizing the final, the amount of Gaussian which is present in the possible data. Okay, I went to various directions in this respect. First of all, we were looking at the mass function, okay, or if you like, the number density, which is one way of probing non-Gaussianity. There are some papers on that respect. We had a prediction for the non-Gaussian mass function, which is being compared with embodied simulations. It works very well. There were some, let me say, complicated improvements, but at the end of the day, the formula remains very, very robust in that respect. And then we had a discussion about for instance, two-point function, et cetera, which is at the basis of what has been done later by many groups, including ourselves. The group in Zurich and many groups are really constructively focusing in this direction. Let me just say a few words about that, because at some point it was a very important paper by the et al. 2007, in which they showed something that was there in simulations. That is, there is a term going like k2-2 in the non-Gaussianity bias, which is one of the possible ways to search for Gaussianity, a very powerful technique. Here we should open a discussion on how k2-2 actually means in terms of going to very large scales. Okay, but in any case, that is a very important result. Let me tell you what Licia Verde and I did a few months later. We just said, I mean, in my formula for the endpoint correlation functions of peaks, okay, I should have had this effect hidden, okay, and it was there. So I took a formula which I had in my 1986 paper, in which we showed that the correlation function of peaks is related to the exponential of all the correlation function of the Riemann distribution, and we succeed to find our own formula for this term with some differences, some improvements compared to the Riemann formula, even though absolutely they were number one in that respect. But I mean, I think that we gave a very important contribution in that respect. Okay. Recently, people are going on in this discussion, making use of this k2-2 term in bias, and also making use of the effects on the bispectrum the gas distribution. Among the various papers, there's this one by Giovanni Cabas et al., which we showed in our Cosmology Journal Club a few weeks ago, and they get these bounds are local. Sorry, I forgot which is the difference between the two results. Okay. Scale dependent bias only on plus by spectrum for local parameter Gaussianity. As you see, it's consistent with 0. Okay, it's consistent with 0. The error bars are larger than those that you can find in from the CFB. Okay, but of course it's important to go in this direction, and there are very important prospects in this direction. Spherics is the most important future prospect, and which is expected to probe values of FNL of order 1. That's why the discussion on whether you do have a GR FNL term is relevant. Okay, because either is there, it's not there, but we are going to arrive to a moment soon in which we will be able to probe this kind of effects. Okay, there has been a discussion which started more or less 5 years ago on whether some terms which are related to so-called consistency relations are physical or not. Okay, as I told you, we had got this kind of result in 1995, then in 2001, and there was this important paper by Maldacena, which gave rise to the particular species form which is written down here. The issue is that you have this epsilon, which at the end of the day is related to the tensor scalar ratio, so we know it is a very strong constraint. And then we have this term here, 1 minus ns, multiplying a local shape. Okay. So since we have very good constraints on the field, 1 minus ns, we can put these constraints there and see what is the expected value of this non-Gaussianity, which is very small, too small to be seen in CMB and isostructure structure data, but from the point of view of, in principle, something which is important to understand. There have been various claims that by making some non-linear coordinate transformation, you can cancel the term, and there is one-to-one connection between this consistency relation and another term which is present in the structure distribution, which is called the GR-FNL. Okay, either you cancel both, both remain there. In a recent paper by Luigi Pilo, Rocco and myself, we showed that the cancellation is there only in the exact limit k equal to 0, which is related to Weinberg theorem for adiabatic perturbations, but only in that limit, which is of course unphysical. In all the other cases, you can perform whatever transformation you want, but the effect is gauge invariant and it remains there. There is a connection to the discussion with a recent paper by Jayur, Hermes, and others, which is quite important. I don't think we have achieved full agreement among the people working on that in that aspect, but the situation is changing and people are more open to discuss this than they used to be 5 years ago, I should say. Okay, but I really insist that in my opinion, the effect is physical, and in 200 years from now, we will be able to serve it. But in the case of lattice structure, the effect is close to a moment at which we will have to discuss about its physical relevance. Okay, that this is the term which I wrote down here. Okay, FNLGR equal to minus 5/3, which comes from very similar reasonings, and I think it's very important to rediscuss that. To those who don't agree with me, I would really encourage them to read in detail this paper, because in this paper we show step by step that the cancellations which have been claimed by various people have been miss one term. Okay, and that one term is crucial because you cancel from term A and you recover the term from term B. Okay, so the sum of A and B remains gauge invariant. Let me now go to a different subject, which is related to the second part of this talk. Okay, third part of this talk. Okay, prospects for primordial gravitational wave background detection. Okay, now of course, given the constraint that we have in the largest possible case from the CMB, it's very hard to be able to detect gravitational waves of primordial origin and inflation energy with LISA or like Virgo or the Einstein telescope. Okay, but you may achieve that situation if you take a blue spectrum of gravitational waves. Let me tell you something which I always try to remember to people. In 1992, people, when we started to have the COVID data, there was discussion on having the scalar spectral index different from 1. Okay, and because we realized that it was possible to have NS less than 1, as we know very well nowadays. Okay, but at some point people said, well, why not consider also NS larger than 1 or NP larger than 0? Okay, then at some point people didn't know how to call this power spectra. Some people call them anti-tilted. Some other people call them inverted. Okay, then with Francesco Lucchini and Steven Moiras, I remember we were exactly in the same room where I am now. They said to me, but this name is really bad. Why don't we call them red and blue? Okay, and we wrote that in a paper. Okay, it's written in a paper. And this terminology is so simple that everybody bought it. So everybody now calls them red and blue spectra, but unfortunately, people don't know that these names were invented by our group in 1992 or 93. Okay, so I'm very proud of this part that everybody now uses this. So I'm talking about blue gravitational wave spectra. Okay, this is important for the later purposes of that. Okay, one of the possible prospects is that of looking not only at the monopole curve in the gravitational wave background, but also at higher multiples, that is, at anisotropies of the gravitational wave background. So, of course, if you want to look for anisotropies, first of all, to see the gravitational wave background itself. Okay, but as soon as you will observe the gravitational wave background, that is the monopole, in some cases you start to see at least the lowest order multiple. So it's very important to look at this idea. Okay, so we start to look at this idea 2018, if I remember correctly, and there were a number of papers written before on non-Christianity in the gravitational wave background, which happened to be wrong. Okay, and then we tried to understand why they were wrong. And we found actually a couple of wonderful papers which had not been noted by people. One was by Alba and Madasina in 2016. I should tell that when we discovered that paper, okay, we realized that it only had 2 citations, which is very rare for Madasina, actually. Okay, and the first quotation was by us. Okay, and but it contained in a very synthetic way a very important amount of information, okay, which we can consider to be the basis for the later discussion. Then there was a nice paper by Contardi in 2017, which also went in the right direction. And then we had a series of papers that you can find by Bartolo, Andrewzardone, myself, and many others in our group. I'm going to say something more about that. So anisotropy in the cosmology gravitational wave background are important both at its production and by the propagation of these gravitons through the large-scale scalar and tensor perturbation in the universe. Note that the first contribution, that is the imprinting, is not present in CMB radiation because the universe is not transparent to photons before the combination. So there is a very important caveat, there's a very important difference between the graviton background and the photon background. Okay, in the photon background, the initial conditions are completely washed out, because of the large optical depth. Okay, prior to the combination. In the case of CMB, of the graviton background, what happens is that you may look at the initial conditions. These are not being conserved, okay? Because right after the production, gravitational waves are decoupled, okay? In principle, suppose that there was no inflation at all in the universe, and then you had only production of gravitons at the Planck era. In that case, we would see, if we were able to see that background, we would see, you know, the anisotropies, the initial anisotropy of the Planck sphere. Okay, unfortunately, there was inflation in between, but that's very important. Okay, we are sensitive to the initial condition, which of course opens very many possibilities to understand a number of things. Okay, so we provide a new method to characterize cosmology stochastic gravitational background through its possible deviation from Gaussian statistics too. In particular, it will become a new probe for primordial non-scientific large-scale cosmology perturbations. Okay, let me say something more about that. The idea is very simple. We said, okay, we have this graviton background. Okay, the frequency of the underlying gravitons is much higher than the frequency of the perturbations over which this gravitational wave background travels. Okay, so we are in the geometric optics limit. Okay, and everything is all the rules are respected in that respect. And the contributions to this anisotropy, as I told you, come from what happens at production, which is hidden in the case of the photon background, and due to the gravitational wave background propagation to the observer, which passes through both scalar and gravitational perturbations and gravitational wave perturbations. Okay, because they are perturbations of the background at the end of the day. Okay. Also important is the fact that this background also carries information about frequencies at production. Okay, which in the case of CMB, since you have a thermal distribution, is completely forgotten. Okay. So let me see. Initial conditions, propagation for scalar modes, propagation for tensor modes. Okay. There are other interesting aspects of this idea. First of all, since gravitational decoupling in the case of inflation production mechanisms basically responds to the moment at which gravitational waves left the horizon of the inflation. Or if you prefer, you can make the assumption, the convention that it corresponds to the end of inflation. Okay. At that time, there were still many ultra-relativistic particles which later on decoupled, okay, which are similar to what happened in the case of neutrinos, massless, ultra-relativistic neutrinos prior to photon recombination. Okay, so in this case, we are sensitive to how many decoupled relativistic degrees of freedom we have had in our underlying model. So it depends upon the particular model, particular physics that we have. We have a paper on that, which you can find all the details. I told you before that if you succeed to find a monopole, then at least for the lowest order multiples, you should be able to get a detection. So don't believe that it's something. It's science fiction, something that will become possible as soon as you will see the monopole contribution. But then I'm going to tell you something which is quite important in our in this respect. Okay, so that is a prediction of the gravitational wave background anisotropy angular power spectrum. Okay, and you see that there are a number of obvious terms like Sachs-Wolf, integrated Sachs-Wolf. Of course, we don't have all those terms which have to do with the right-hand side of the Boltzmann equations, and in the case of photons, that is those which are related to the Compton scattering term that we don't have here. But there is a very important aspect too. The important aspect I want to tell you is that you may have cross-correlation with the CMB, okay? Because in spite of the fact that I have gravitons on one side and photons on the other side, both gravitons and photons pass through the same perturbations, underlying perturbations of the ground. So they pass through the same scalar perturbations and pass through the same gravitational wave perturbations. Okay, and that implies that leads to a cross correlation among these observables. Okay, these are this is the predicted map of the gravitational wave background. This is the observed map of the CMB. Okay, and what we did was to, this paper is appeared in PRL, was to show the expected cross correlations, which are written here, and we also did another very nice exercise, which is to perform constraint realizations. Because suppose that we go to a very large case, Sachs-Wolf for one object, Sachs-Wolf for the other object, ISW for one object, ISW for the other object. Okay, and the underlying scalar perturbations are the same. Okay, so in the largest case, okay, I can tell you, I know what is the map of the CMB. Given that map, I can make a prediction of what I'm going to serve if I will see the monopole. Okay, if I will see the monopole, what I'm going to serve for the gravitational wave background, but not statistically, but locally. Okay, geographically. Okay, that's very important to be mentioned. I think I have a plot here. Okay, that is the plot. Okay, so CMB, constrained simulation of the stochastic gravitational background is same resolution. Constrained simulation in the case of I don't remember. Okay, constrained simulation in the case of maybe Lisa, I forgot frankly, this Lisa or Einstein telescope. You see that the resolution is much lower. Okay, but the important point is that while this result very much depends on whether we're going to observe the primordial gravitational wave background, there is another fact, which is suppose that we have astrophysical gravitational wave background, which we will have, because the astrophysical gravitational wave background is simply given by the sum of those events that we are not yet able to resolve. So the astrophysical gravitational background is there and is going to be detected by, for instance, LISA or other interferometers. Okay, we can do exactly the same analysis. Okay, and in this case, we know that this background is going to be seen, and this is our prediction for what you're going to see in the sky. I want to mention very rapidly three more effects. How much time do we have left?
I would say maybe 5 minutes.
Okay,
if that's okay.
Absolutely it is. Okay, this is to advertise some importance and what I work in the mid 90s. Okay, I started to look at second order in GR, and among the new effects that we found was that of course, what happens is that if you go beyond linear order, you start to mix up modes, not only in the sense that a given wave number takes contribution for different numbers, but also in the sense that a scalar perturbation, linear order, gives rise to scalar vector and tensor perturbation second order. A tensor perturbation linear order gives rise to vector and scalar perturbation, etc., etc. So there is mixing also in terms of the type of modes. Okay, one of those effects, which was written in my paper in actually the very first paper was in 1993 actually by us. We showed that we have this what is now called scalar induced gravitational waves. I remember that I gave a talk on this point in near to Potsdam, in the place where then the Albert Einstein Institute was built up later on. And Kenny Tomita was there in the audience, okay? And he told me, after my talk, he came to me and told me, Sabino, I've written papers in 1967 about the same thing, which I didn't know, frankly, because they were very difficult to find in literature, okay? He sent me his reprints because it was impossible to find them. And after that, I always quoted these very nice papers, wonderful papers, written, I think, 3 papers in which he considered all possible mixings, okay? Then later on, there was some important papers by Baumann et al. And Anand et al. 2007. And nowadays there is an industry. The industry is there because when I proposed this idea, people said, well, but the effect is very small because, you know, density perturbations are already small by themselves. You have to go to quadratic order, these gravitational waves are very small. But nowadays, the situation has changed because the density perturbation, which gives rise to primordial black holes, can be very high on some high frequency scales, high wave number scales, and that gives rise to enhanced gravitational waves, okay? That is one point which I wanted to mention. I'm working with Andrewzardone and Chiara Testini in that respect. We hope to be able to have our own contribution in this result in the PTA frequency range, I should say. And then I want to mention two more things, especially one, okay? That is something which I also had in my paper in 1997, and then 93, sorry, 97. And then that was also in a paper by Tovita in 1971, which is a completely opposite effect. Gravitational waves producing scalar perturbations. Okay, that is very simple to understand. I mean, you see the equation here, which is the one which better shows the physics, the underlying physics. Okay? So the left-hand side, the delta 2, so it's a second order density perturbation. Okay, it's the standard equation for scalar density perturbations in a matter-dominated universe. Suppose that we take matter domination for simplicity. Okay, the right-hand side is the square of the time derivative of the gravitational wave perturbation. Okay, but this object, you can recognize it, is the energy density of gravitational waves. So what you're saying is that fluctuations in the energy density of gravitational waves, which is of course an unavoidable second-order effect, are a source for scalar perturbation. Okay, we studied in detail this idea in a recent paper by Prita Bari, our PhD student, Angelo, Nicola, Daniele, and myself, and we have a second paper in preparation, which we extend to a more complicated situation, let me say. And we found some interesting results. The interesting result that these newly born perturbations, okay, propagate, evolve in time exactly like standard scalar perturbations. okay, which is in a sense unexpected. Okay, but they have a very important difference. Basically, the idea is that, as you know, gravitational waves are constant outside the horizon. So in the previous formula, outside the horizon, you have zero source. Okay. Then, as soon as they enter the horizon, the time derivative started to be zero. But then, after they enter the horizon, gravitational waves, as you know, behave like photons. So they decay in amplitude and they suffer redshift. Okay. So basically, these dense perturbations get a kick at any time a given gravitational wave enters the horizon. Okay, and then after that they evolve like standard density perturbation. That's why they evolve like that. But the important difference is that outside the horizon don't give any contribution. Okay, so for instance, you wouldn't have for these new type of perturbations any effect on the lowest multiples of the CMB, those which come from perturbations outside the horizon. We say. Okay, we have examples here of different types of initial spectra for gravitational waves. We took blue spectral gravitational waves. We took bumps in the power spectral gravitational wave as it happens in axion models of inflation and similar situations, and we found something quite interesting for practical purposes. The very last issue which I want to mention, but I'll do it very, very rapidly, is about vorticity. Vorticity is another effect of going towards second order. You may tell me, but vorticity is conserved, so it's forbidden to give rise to it. Absolutely correct. But there is a tricky point. The tricky point is that when you go to second order, okay, vorticity is conserved. So unless you have some dissipation effect, there's no way to generate vorticity. But suppose I have a multifluid. At second order, you do generate a vector mode, for instance, the one connected to the zero I component. I mean, of course, you know that you can have a case observation, so you can move it to some other parts of the metric. But suppose that I focus on the zero I component, which is the same term which gives rise to this called dense steering effect. Okay, it's a vector mode, which appears there if I go to second order. Then suppose I have electrons, protons, dark matter, electromagnetic field, neutrinos, etc., etc. Okay, the overall vorticity has to be zero. But the zero vorticity can be the sum of different algebraic vorticities different from zero with different sign. Okay, and that is what happens. Okay, so because of that, you do succeed to have rotation of electrons and protons. Okay, if they're not tightly coupled, okay, that generates a magnetic field, and that magnetic field is there anyway. Okay, so it's an unavoidable mechanism to produce magnetic field in the early universe. This magnetic field, unfortunately, is small. Okay, we made the first prediction in this paper in 2005. Then there was a numerical analysis made by I think it was this paper, not the only one, but I mean Feno, Pitrou, and Martens, and some other papers, which they improved because they really use a sort of second order transfer function. The numbers more or less agree. Okay, unfortunately, the technique, the level is low, but we should consider the possibility that in principle there may be models which succeed to increase the amplitude of perturbations, density perturbations, and then I can increase also the amplitude of the produced magnetic field. Okay, let me conclude this talk by telling you that first of all, CMB and circumstantial data fully support the detailed predictions of the standard cosmological model based upon Professor Walker, Lambda CDM, initial condition of inflation. The direct detection of the cosmological stochastic gravitational wave background, both of primordial and astrophysical origin, together with its anisotropy, will provide a unique probe of the early universe, as well as of modified gravity theories, which I didn't have to mention in this talk. Cross correlations of the stochastic gravitational wave background, the CMB as such, will open a new window to search for new physical effects and constrain our cosmology with fundamental physics models. And in full generality, going beyond linear evolution opens up a Pandora box of new unexpected phenomena which deserve being explored and fully exploited in the future. I'll stop here.
Very good. Thank you very much, Sabino. Very nice talk. Yeah, so let's open up to questions. Please raise your hands in the Zoom. So for the moment, I only see the claps from any questions. We still have we have time, like maybe 10 minutes or so.
So Sabino, the cultural war between blue and red state started already in 1992.
Absolutely, absolutely. Because right after the Kobe result. Yeah.
That I didn't know. Yeah.
Absolutely, absolutely. I should tell you something which is quite. At that time, we didn't have internet. We only exchanged emails. Okay, and the way we got the information about the Kobe results was that we got an email, in our case by Adrian Melot, and the sentence which he quoted from the collaboration was that Kobe has detected anisotropes which are well fit by a Gaussian spectrum. Okay, so if you read the Gaussian spectrum, you mean, what do they mean by Gaussian spectrum? What they actually meant was that they had fit the anisotropes taking the power spectrum to be a Gaussian. Okay, which is actually forbidden by the fact that the correlation factor doesn't go to zero. Okay, but you know, for some time, are they really also analyzing the statistics? No, it was a Gaussian spectrum, but that was the only message we got. Okay, and of course we had the sigma of this Gaussian. We had to start to elaborate on consequences for cosmological models.
I see. One question. So this model for with the gravitational wave models with the blue spectrum, this model has a the scalar fluctuation with the red or blue.
You can have both.
Okay. So it's independent.
Needless to say, I don't want to cheat. It's very difficult to get these gravitational waves with that blue spectrum.
Okay.
We wrote a long paper with Nicola Bartolo and Giulia Capuri, who's now a PhD student at CISA, in which we used the most extended class of effective theory models of single field inflation. Okay. And we were able to show that there is a range of parameters which you do succeed to have this blue spectrum. Okay, and when you have this blue spectrum, of course you're violating the consistency relation. Okay, and basically you need H dot to be positive. Okay, so you have a negative epsilon if you like. Of course, well, it's something to be discussed. Okay. It's not forbidden. I mean, it's something which is hard to achieve. It's not forbidden. You know, that was something that people studied many years ago in the context of pre-Big Bang theory. Okay, because if you do a mapping between Jordan frame and Einstein frame, this H dot larger than zero, sorry, H dot larger than zero, not negative, positive. Sorry, larger than zero corresponds to, if you change frame, corresponds to a contraction. Because you cannot just use standard single field inflation to get that. It's impossible. It's forbidden.
Very good. So I also have a question. So at the end, so you have explored many of these second order sourcing of perturbations. And at the end, so if somebody now comes and says, okay, which one is the one that has the most violent, the most remarkable, you know, in terms of magnitude, the most important effect? Because you discussed, for instance, the sourcing by gravitational waves squared. That a priori, I think everybody would expect it to be extremely low. So I understand that the mechanism, because it's completely zero outside the horizon and everything is particular. So it has some specificities that would allow you to distinguish it, but the amplitude is so small.
It depends. It depends. I perfectly understand your point. That's the reason why I waited for something like maybe 30 years, 25 years to start to discuss again these sort of things. I mean, but I think it's very important in principle, first of all, and then there are cases in which you do succeed to do it. Okay, let me tell you. Let me first of all make an historical remark. Okay, when I started to look at non-Christianity, okay, I remember that I had to fight against the majority of people in the audience telling me this university is so small, okay, it's impossible to get it, okay? Then at some point people said, well, but you can have that exception. And then the number section becomes larger than the number of cases in which you have negligible universality, okay? Second order, scalar-induced gravitational waves, okay? Also in that case, when I gave talks in the 90s about that, people say, oh, that's absolutely correct, but why do you care? The effect is tremendously small. But then what happened was that people started to look at primordial cause. In the case of Bauman et al., the idea was related instead to the epirotic model, okay? And what happens is that in those cases, you succeed to have large density fluctuations, which are not in contrast with the CMB constraints, okay? And this gives rise to large enough gravitational waves. Right. Similar story here. In this case, what happens is that, okay, we consider three cases. One case in which we have visible spectrum, then you can tell me why it's not so easy to get them. I may agree with you, but that's a possibility that people consider. Another case is bumps. Okay, these bumps are very characteristic of axial inflation. Okay, and the amplitude that we took for this model is consistent with CMB constraints. In other words, the point is that there is a range of values of the wavelengths, okay, in which you have poor lasting structure constraints. Okay, that is basically between, let me say, if I take the CMB, okay, the CMB gives you an indirect constraints on density fluctuations up to maybe 100 megaparsec, no, more than that, okay, 1000 megaparsec, okay? Then in between that scale, okay, and those which start to be probed by present-day galaxy surveys, okay, you have few constraints, okay, few lasting structure constraints. So on that range of quite freedom, quite a large amount of freedom, okay, and that is the one we exploit, okay, and that is the one which is exploited by people who consider bumps in the case of axial models of inflation. So to be very clear, okay, the amplitudes and wavelengths that we considered are those which is standard to consider in the case of axial models, and we do get some interesting signal there.
Okay, right, but it wouldn't be the vanilla model, so to speak.
It wouldn't be vanilla, absolutely.
Right. I mean, you have to go someplace outside of the
absolutely agree with you.
No, so I'm not saying it's irrelevant. It's very relevant, but it's just to get a taste. So for instance, so you would say that the number one thing to look at is scalar square source for gravitational waves. That would be maybe the most promising type of second order effect.
Given the present situation in terms of the models that people are considering.
Yeah.
Okay,
yeah.
I agree with you.
Very good. Yeah. That with that extra sentence. Yeah.
I mean, my message is always, please keep your eyes open. Yeah. Because models may change, and there are regions of the parameter space which have more freedom than you expect to have.
Very good.
And it's another important point. For many years, I told people, I mean, I like to write a paper whose title is "Can gravitational waves give seed galaxy formation?" Okay, which is very, very provocative. Okay, yeah. And the answer is yes. In principle, yes. In practice, it doesn't work, but the answer is yes, which is really unusual, to say the least. Okay.
Yeah, but I mean, it's energy. So with gravitational waves, you can also form black holes.
Energy.
In principle, you can go crazy places. The question is how
exactly.
Yeah, realistic or something. With
absolutely, I could agree with you. But I mean, we should keep our eyes open to new ideas and new.
No, but very interesting. That was to get a more quantitative kind of feeling. Very good. Do we have any other questions? I think we're approaching the usual end. So I think if there are no other questions, let's thank our speaker again one more time. Thank you very much, Sabino.
Thank you, all of you.
Really a pleasure. And yes, let's find another time maybe to discuss more in depth. And other than that, I wish everybody a happy weekend. And thank you one more time. Goodbye.
Bye, everybody. Bye. Thank you very much.